Hello everyone, I'm Sandeep Banik. I'm a PhD student at Michigan State University. My area of research is primarily on security of cyber-physical systems. Today I will be presenting my work on determining secure routes on graphs using game theory, which involves solving a special structure of dynamic games with stopping states. So we start off with a typical path planning scenario which consists of an agent that wants to go from a source vertex S to a destination vertex, let's say T. As we see, there are three possible routes connecting different vertices to reach the destination. We are interested in answering the question, how secure a route is under an attack. A typical attack that an agent encounters is either a cyber or a physical attack. Now, one might ask, why should someone even care to solve such a problem? An agent, such as a connected autonomous vehicle, an unmanned aerial vehicle, or any general system, can be equipped with an ability to counter or disable an attacker. However, these systems are generally energy-constrained devices and may be running on batteries or have limited power. So then arises the question of balancing between disabling the attacker and conserving the energy to complete the mission. I believe this is important today for services such as Waymo's taxi service or Amazon's Prime Air using drones for delivery of goods. The problem formulation consists of an environment which is modeled as a graph G. The graph G consists of a set of vertices and edges. Now, looking at the graph, let's focus on an edge E connecting two vertices belonging to a feasible route. We say that the travel between two vertices consists of several stages called KE. Each stage is associated with a stage cost matrix S subscripted by the corresponding stage, like S1, S2, and so on. In this work, we use fixed stage costs across all the stages on an edge E. Now, what do these stage costs represent? Well, the stage cost represents the payoff matrix between the defender, which is the agent, and the attacker. Therefore, we model traversing over an edge between two vertices as a multi-stage zero-sum game between the defender, being the row player, and the attacker, the column player. The defender-attacker take actions simultaneously, making this a simultaneous game. We term this whole setup as an edge game. After defining an edge game, we impose the limitation of an edge attack in the graph. Such a limitation is imposed because an attacker is usually resource constrained. Additionally, once an attack is detected, the defender is aware of an attacker present in the current path, which makes it cautious. Using the edge game and one edge attack, we construct a zero-sum game called the metagame. The metagame is defined over feasible paths and edges. Now let's focus just on the edge game. The payoff matrix, being a 2 cross 2 matrix, corresponds to two actions for the defender and attacker. So the attacker can choose either to attack and no attack given by A and NA. Similarly, for the defender, we abbreviate D for defend and ND for no defend. Given this information, let's see how a dynamic game propagates as a result of the actions chosen by the players. We start off with the case of no defense and no attack leading to this leaf node. Similarly, with no defense and attack, we branch to an alternate leaf node. This is also observed for defend and no attack, as you see in the figure. Now finally, we come to the action of defend and attack leading to this state known as a stopping state. The stopping state represents the defender disabling the attacker. That is, if an attack and defend occur simultaneously, we say the game stops. Now, you might ask, what if I want the game to continue and only stop when it occurs concurrently, twice as shown, or thrice, or any n number of times? We capture this using the parameter L, and for this work we assume L is equal to 1 as illustrated in the game tree. Now for the other leaf node, the game continues. However, at every stage there will be a stopping state as a result of the action defend pair. And the game tree branches till it reaches the final stage KE. The abbreviation V here represents the expected payoff corresponding to the stage, and we will see next how do we obtain these. Here we determine a method on how to solve the edge game. The edge game is a multi-stage zero-sum feedback game. I emphasize feedback here because at any given stage, the attacker and defender are completely aware of the game state. That is, what actions of both the player led to this current state. At any stage k, the expected value is defined through this recursive equation. The term D is the decision matrix as a result of the game structure. From the game tree, you will observe that the value of the next stage is propagated back to the previous stage only along a set of nodes because of the stopping state. Now S is the stage cost matrix which we saw earlier between the defender and attacker. The expected value of the game is determined by solving for a mixed Nash equilibrium, and recursively solving the game from the final stage to V0 leads to the value of the H game. Let me talk a bit more about the stage cost matrix S. We consider a simple and parameterized version of the stage cost matrix parameterized by R1 and R2. S11 is the cost of defense, and we assume this is constant over the actions of the attacker. Basically, this means that the defender will have to pay a constant price for using a countermeasure if the attacker chooses any of its actions. R1 is the ratio of the security loss S21 to defense cost. S21 corresponds to an attack with no defense, that is, how much would the defender pay in case of security loss. R2, on the other hand, is the ratio of the mobility cost to the defense cost. The mobility cost is the minimum effort the defender expends on going from one stage to the next. If we assume S11 to be unit defense, we need to satisfy the following properties. The first property says that R1 is greater than 1. That is, there is some incentive for the attacker to even choose to attack when the defender does not defend. And second one says that the mobility cost cannot be higher than the defense cost. Basically saying if the defender cost was cheaper, then the agent will always choose to defend. We come to the main result of the edge game. As we saw earlier, the value at any stage is a recursive equation and it can be easily solved using backward recursion. The interesting thing is that it leads to a simple expression at any stage k as a result of the action space and fixed stage cost matrix S. Det S here represents the determinant of the stage cost matrix S. We start off with the value at the final stage being equal to 0 and move till we reach V0 representing the value of the edge game. Similarly, using parameterized stage cost matrix, we get the following form with the same initial condition. The figure illustrates the value of the edge game for stages KE. As you see that the value of the edge game V0 keeps increasing with increasing KE, but the stage cost entries shapes the rate at which it will grow. With R2 being equal to 0, that is no mobility cost, the stage cost grows sublinearly, and with R2 equal to 0.5, it starts becoming linear with the number of stages. Therefore, as R2 increases, the value of the edge game becomes linear with stages KE. Solving the edge game also provides us with the policy for the defender and attacker. This is a function of the stage cost entries and the expected value at the current stage. We also obtain the defender policy for parameterized stage cost. From the figure, we observe the policy of the defender for the defend action D at the start of the game. You will observe that with increasing stages, the probability of defending goes down. Now, as R2 goes from 0 to 0.5, we see that the probability of defending at any stage keeps decreasing. An interesting fact to note is that with increasing stages KE, the defender starts with no defense for all possible configurations of R1 and R2. The attack policy looks very similar to the defender policy with similar observation to start off with no attack with large KE. The main takeaway from the policy we see is that both the defender and attacker become increasingly active in the later stages of the edge game. Given that we have found a solution to the edge game, let's see how do we tie it back to the metagame. The cost associated with an edge is given by WE, which depends if the edge can be attacked, leading to the value of the corresponding edge game. Alternatively, if the edge is free from an attack, then we see that the defender chooses not to defend, leading to the entry of S22, that is, the defender just pays the mobility cost. Let us consider one of the paths in the given graph. The path is indicated by the directed dash edges. We say such a path is composed of a set of linked edges connecting a bunch of vertices till it reaches the destination T. Now, the cost of a path is given by the summation over each edge cost. The zero-sum metagame is defined over feasible paths and edges. Let's see how do we construct a row for such a metagame. For a given path, we determine the corresponding path cost conditioned on the attack over the feasible edges. Here you see we also determine path cost conditioned on the edges not belonging to the current path. Therefore, given n feasible edges and m feasible paths in a graph, we construct the metagame entries. The result of solving such a game gives the probability with which a defender picks a path under worst possible case of attack, and similarly which edge must the attacker pick over the possible paths. The metagame is solved using linear programming, and you'll find tons of literature and references on how this is done. We also developed a simple shortest path heuristic under the same constraint of an edge attack named SEA. The algorithm is as follows. Given a graph, we first solve for the edge game on the feasible edges. For illustration purpose, let us consider a simple graph and assume the number of stages to be 3 and 6 as shown in the figure. For each of these, we solve for the edge game. We then use them as edge costs for the shortest path algorithm like Dijkstra and determine the shortest path. Now we have found the shortest path, we determine which edge attack has the maximum effect on the corresponding path cost. And this forms the heuristic solution. We compare the solution of the metagame with the shortest path heuristic and observe that the cost is much lower, along with an important observation that the shortest path is not the safest. We solve the metagame over all feasible paths and edges, and for a fully connected directed acyclic graph with n vertices, we see how large the size of the metagame grows. Therefore, here we observe how does the solution of the metagame stack up against SEA. First, we see the time performance for a given number of vertices. We plot the time average of the metagame and the SEA over 100 runs. We observe the metagame takes a significant amount of time compared to SEA, and although there is some benefit in sparse setting, the dense or fully connected graph performs poorly with increasing vertices. Next, we see the cost performance of the metagame and SEA. Here we see that with increasing sparsity, the solution of the SEA reaches closer to the metagame, and for a dense or fully connected graph, it saturates. So one might want to believe that the solution of the metagame is comparable to SEA. However, these statistics don't convey the full story, as we will see next. Now we compare the metagame path with SEA to determine how often does the metagame choose the shortest path. For a sparse graph setting, we see the probability of choosing the shortest path increases with the number of vertices, given that the sparsity of the graph remains fixed. However, when we look at the fully connected graph, the probability of choosing the shortest path decreases by a large amount with increasing vertices. This indicates that even though the cost might reach saturation, there exist alternate routes which are secure as compared to the shortest path. Therefore, we conclude that the solution of the metagame is risk-seeking in sparse graph and risk-averse in dense graphs. So we started out by asking the question, in a graph G where an agent wants to go from a source vertex S to a destination T, what is a secure route? We showed how can one model the travel between two vertices, balancing between security and mobility as an edge game. Next, we used the edge game to determine a secure path and a corresponding malicious edge. Finally, we used the edge game again to determine a fast and simple heuristic to determine a corresponding secure route. Finally, coming to the current and future directions, the current work under review is the inclusion of multiple attacks in the edge game. The game tree illustrates where the stopping state is reached after two concurrent attack-defense action pair. We also worked on asymmetric information for either the defender or attacker, that is, what would happen if the defender was unaware of the game state at any stage, then how would the solution look like? Finally, we can also explore a non-zero sum edge game where the attacker and defender might care for different objectives. I conclude my work here, and I hope you enjoyed my talk. Please feel free to ask any questions.